All right, welcome back everybody. We're gonna have a little bit of a shorter video today. That's just because I want to give everybody a bit of time to get used to computing Fourier transforms, computing Fourier series, just getting comfortable computing these objects as well as their motivations and getting used to why we use them. So in the last video, we finished by covering these sorts of objects, an exponential of a derivative operator, and we said because of the Fourier transform, we can actually write these as an exponential of a function, right? In this case, the function is negative z squared minus w squared, where z and w are the conjugate variables of x and y in the Fourier space. So that's really important for Fourier transforms, but to have any sort of idea of what this may actually compute to, right? This is a very important computation to try to make. So we want to know what would this actually compute to. If I tried to compute it, we're going to have to get used to computing Fourier transforms. So that's what we're going to spend today on. And if you're in any sort of standard ODEs course, you probably covered the Laplace transform in the way that 99% of the time you were computing a Laplace transform was with a table. Okay, so we're going to have the same sort of deal with the Fourier transform, where I've got a table, and on the left-hand side, we're talking about where we start, and on the right-hand side, we're talking about where we end. In fact, the way I've set up my table is that I've split it between, these are just kind of operations we can perform, and where they end up. Underneath the Fourier transform, and then down below in the second section that I've walled off, this is, functions, real functions, or specific functions, and then the specific functions transforms of specific functions. So really you want to think about using some combination of the top half and the bottom half. In some way, a lot of the common Fourier transforms are going to be, okay, it's going to be, the function e to the negative absolute value x, but perhaps it's been shifted, and perhaps there's been a couple derivatives taken of it, and perhaps there's an invertible matrix that has hit the variable. So it's, some combination of all three of those. Let's look at maybe what an example of that would look like. Would be something like e to the negative 2x minus 1 plus 3y minus 2 plus z plus 1, and then this is all in absolute value. So like that would be one example of, not only did we take an invertible matrix on this, these are the scalings of 2, 3, and 1, but we took a shift. Those are the shifts of negative 1, negative 2, and plus 1, and then we're using e to the negative absolute value x. So, and you could imagine you could also take a derivative of that. And so you just have to, you kind of find the function that we're dealing with on the bottom half, and then find the collection of operations performed on that function on the top half. And then you have to combine, okay, that specifically would go to this ugly looking object. Each one of these goes to each of these objects. And then if you combine them all correctly, you can find your Fourier transform. This is very similar to what you were doing with Laplace transforms. I do want to comment, though, at the beginning I give a remark on my definition, and this is a similar comment as before. In fact, my definition isn't correct right now. It should be d over 2 and d over 2. But as before, a lot of different definitions of Fourier transforms will use different coefficients up front. They'll push the 1 over 2 pi onto one or the other side. And definitely keep in mind this will be d over 2. I'll make that switch pretty soon in the book. And there you can see I've just defined it in higher dimensions. If you decided to jump down to one dimension and you didn't boldface anything, then of course the dot product becomes just a product, and the volume form just becomes dx. The dot product becomes a product, and the volume form becomes dy. Something that's pretty useful here that I've commented on before is that the inverse Fourier transform is the complex conjugate. And keep in mind, complex conjugate just means that I becomes negative I of the forward Fourier transform. And this is useful for our table. If we ever decided we wanted to do an inverse transform, what can we do? We can say that this is the Fourier space. This is the natural space. And what do we have to do is we have to find every I. So every I that shows up, we're going to replace it with its negative. So that negative I becomes positive I, this positive I becomes negative I, this positive I becomes negative I. And really everything on the left should have hats on it, and everything on the right should not have hats on it. So that's what we want to think if we ever want to use this table in the reverse direction. Same on the bottom here if we see any i's, but thankfully these are mostly good. That should be a minus I then. And that should be a minus I. We're going to do the inverse transform instead. So that's how you can use this table actually as a two-way street if you want to. And then I'll make a couple other comments before we get into these calculations. The first comment is that this delta that you're going to see in the table is the Dirac delta function. You should have seen this with Laplace transforms. It's very common with Laplace transforms as well. You can think about this as the quote-unquote derivative of the Heaviside step. And that only applies in one dimension. In higher dimensions, there's not really an analog to the Heaviside step function. You can imagine, because in 2D we can define the boundary of where the Heaviside switches from 0 to 1 in any shape possible, which means that the derivative is now a gradient, and then you have like delta functions pointing in lots of directions. So you can't take that analog in higher dimensions, but certainly in one dimension. You should have covered that with the Laplace transform. But even if you haven't, the way it gets defined is as the following. So if I take some function, phi, and I multiply it by delta, so multiply phi by delta, and technically this is a convolution. You're going to shift and reverse delta by x. So instead of having a y there, you have an x minus y. Then the result of an integral over all of space is evaluation at x. So there's my x, 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 x. So it's that evaluation is what the delta function does for us. It allows us to evaluate functions at a point by producing integrals. Really, it's convolutions. So that is going to be the delta function that we see down here, right when we see it there and there. Either if I'm taking a Fourier transform of a polynomial, we pick up derivatives of a delta function. If I'm taking the Fourier transform of an exponential, we're going to pick up shifts of the delta function. And that's just because the Fourier transform of 1 is the delta function. This is not uncommon with like the Laplace transform. You got 1 over s. The Laplace transform of 1 was 1 over s. Just think about the Fourier transform of 1 is the delta function now. Okay, so that's everything I wanted to cover regarding tables. Now let's actually get into using these tables to compute Fourier transforms. We're going to start with a one-dimensional Fourier transform. So let's try to take a transform of x times x plus 2 of e to the minus x plus 1 squared over 2. So we have to think about what sort of combination, of second half of table with the first half of table gives this. We're asking ourselves a question: what combination of functions over here, along with operations on the functions over there, is going to give us, let's write it out again, x times x plus 2 e to the minus x plus 1 squared over 2. Might have been x minus 1 squared. Let's see. X plus 1 squared. All right. So we're going to try to figure out what's going on between the bottom and the top here. The first thing I'm going to notice is that if I write the bottom, my Gaussian, right? I definitely have a Gaussian up here. In one dimension, the Gaussian doesn't need the absolute value sign on it. So that's a Gaussian, but something has happened to it. What's happened to it? This is actually a shift. Shift of plus 1 on Gaussian. So where's my shift up here? There it is. That shift has a minus sign on it. So when I go to the other side, instead of having a minus on x, I'm going to have a plus there. X naught is a 1. So if I put a plus 1 here, this x naught becomes a plus 1. So what I'm doing is I'm going to multiply. This is going to get sent over to a multiply transform of Gaussian by, how much do we multiply the transform of the Gaussian by? E to the I y times 1. The transform of the Gaussian looked like this, so we'll end up with transform of Gaussian, which itself is e to the minus y squared over 2. So that's going to get multiplied by e to the iy. But we're not done, because we have to play this game with x and x plus 2. How are we going to play that game? So what does multiplying by x and x plus 2 do? So I've got quite a few choices here. A couple of my choices come right here. I can think about all of them as individually mapping over to derivatives of delta functions. If I want, I can map all of them over to derivatives of delta functions. You just have to be careful that since there are two multiplications here, every multiplication on the left-hand side is coming right here. It's going to look like a convolution. I can get away with that because I know that convolution against the delta function is an evaluation. Convolution against the derivative of a delta function is evaluation of the derivative. So I can definitely get there this way if I wanted to. But if I want to be slightly more clever, I have to note that I chose a shift by +1 on the Gaussian term. So if I had a shift of +1 on the Gaussian term, I should include this, or I should find it, the same shift on x and x plus 2. Now how do I find a shift of 1 on x and x plus 2? You just kind of have to force it to be in there. A shift of +1 looks like this, right? X plus 1. What is x plus 1 in terms of x? Well, it's actually x plus 1 minus 1. So there's a shift. What is x plus 2 in terms of x plus 1? Well, it's x plus 1 plus 1. So really I have that sort of a shift happening. And if I want to multiply this out, if I want to FOIL, but I'm going to preserve the x plus 1 terms, let's FOIL that out. It's a difference of squares. Okay, well, it's the factorization of a difference of squares. Is going to give me x plus 1 squared minus 1. So, in other words, x plus 1 squared minus 1 and x times x plus 2 are the same thing. These are absolutely the same object. But it turns out that writing x times x plus 2 as x plus 1 squared minus 1 is going to be extremely useful in comparison when I'm considering a shift, right? Because now I have, if I rewrite my Fourier transform, the function I'm trying to Fourier transform, as this, what can I do? I can actually distribute the exponential, or the Gaussian, and I end up with x plus 1 squared e to the minus x plus 1 over 2 minus e to the minus x plus 1 squared over 2. That should be squared as well. Now if I'm trying to Fourier transform, I know what this is. I've already computed that. We already talked about it. Now I just have to find the Fourier transform of this, where everything is a shift by 1. So it's a shift by +1 of x squared e to the minus x squared over 2. So the question becomes, what is the Fourier transform of x squared e to the minus x squared over 2? And we either go back here, we say, fine, we're gonna take a transform of a power of x, and we're gonna get some derivatives. Or we can think about, actually, how does the derivative, what would something like derivative of x, and actually we're in one dimension, so I can take the true derivative, d dx is e to the minus x squared over 2. What is that? That's x, e to the minus x squared over 2. I'm thinking in this territory. What is the derivative of e to the minus x squared over 2? Well, it's x, e to the minus x squared over 2. What's the second derivative of e to the minus x squared over 2? Well, I have to take the product rule of the first derivative. That's unfortunate. Let's go ahead and do it. So product rule of x e to the minus x squared over 2 gives me, well, actually there's a negative sign up front. Well, one of the terms is going to be the chain rule from the Gaussian. That's going to give me a positive x squared e to the minus x squared over 2. And then the second term is going to give me a derivative of the x out front. It's going to be minus e to the minus x squared over 2. Does this look familiar? I'm going to pause really quick because it's on the video. You should be able to find it. Yeah. So in fact, what we've just calculated is what I've just erased. It's this entire piece. So the second derivative of the Gaussian is that entire piece, except what's slightly different about that entire piece is this is shifted by +1. So all of that work aside, what did we decide about this object here? It doesn't look like it. but with a critical eye, and this is really what's important about computing Fourier transforms, is this critical eye. You know, our job as mathematicians is to take a critical eye to everything. So with a critical eye, this is two derivatives of the Gaussian shifted by +1. And we know how to handle all of those operations with the Fourier transform. We know what the Fourier transform of the Gaussian is. We're going to calculate that first. We then know what two derivatives on a Fourier transform is. We're going to calculate that second. We then know what a shift by +1 is. We're going to calculate that third. So I'm just going to jump up again, up to here where everything's on the board. First, transform e to the minus x squared over 2. Second, transform d squared dx squared. Third, transform shift +1. That's going to be here for number 1. That's going to be here for number 2. That's going to be here for number 3. So let's do that. There's number 1. We start with, use a new color. 1 says, hey, my output is e to the minus y squared over 2. At step 2, we move to the right. It says, hey, actually the output, if I'm doing two derivatives, I'm going to do y squared e to the minus y squared over 2. And then step 3, I'm going to say, wait a minute, I'm actually shifting this. What is a shift? By +1. By +1, I'm going to multiply by e to the I y. And if I wanted to simplify that, I could a little bit. I squared is -1, y squared is y squared, and my exponential rules tell me that this is e to the iy minus y squared over 2. And so this, what we've just discovered, is the Fourier transform of the original function that I was trying to transform. Okay, then moving on to a d-dimensional Fourier transform, we're going to try to find the Fourier transform of sine multiplying by the sine function. It's been dotted on the inside. This is the dot product of some vector v, dotted our actual variable x. So v dot x inside the sine function against the Gaussian. We're going to see if we can find the Fourier transform of that. And this is something to jump back to every time we see sine or cosine in a Fourier transform. We really do want to represent this with Euler's formula. There's not really going to be a better way to transform sines or cosines. This goes back to the series as well, because Euler's formula translates them directly into the objects that we work with in transforms, right? These complex exponentials are exactly the objects that Fourier transforms are built around. So if we can rewrite sine in terms of Euler's formula, we're going to do that. And then what's going on here is we actually take that sine and we multiply it by the Gaussian, e to the minus x squared over 2. And when we multiply it, we're going to distribute that Gaussian to both terms individually, and we're also going to split the fraction up, the 1 over 2i up. And what we get out of this is really two separate terms that are all exponential-like. So we've got two separate terms that are exponential-like. They have the complex exponential term and the Gaussian term, and then this coefficient of 1 over 2i. But the really nice thing about the Fourier transform is that it's linear, right? It's based off of an integral, and we know that integrals can be split at plus or minus signs, and they also pass through constants like 1 over 2i. And so all we're actually really looking at transforming here are these pieces individually. If we can find the transform of each of these pieces individually, then I can recombine them to find the full transform of the full function. So we're going to look at the first one of these, the e to the positive I, v dot x, against the Gaussian. And we're going to jump back maybe to what I had written before, but I didn't explain so great. What we want to think every time we see these functions is we want to ask ourselves the question, okay, is this function a shift of anything? Does this function look like a shift of anything? If the answer is yes, then the transform is going to look like an exponential multiplying that function, a complex exponential multiplying the transform. If the function looks like a scaling, suppose the function looks like a scaling of anything, then the transform looks like, well, it's just this little inverse of the scaling. And if the function looks like it's been a directional derivative of another function, and then the transform looks like this, I guess it's a directional polynomial in this section, right? That's a directional monomial even. In the transform space. And the question is, does the function that we are seeking look like any of these? I think the answer is very quickly no. We definitely don't have a shift. There's no shift there. We don't have any scaling. I mean, perhaps you could think about v as a scaling, but it's not, because we're at higher dimensions, greater than 1. In one dimension, v could be a scaling. And it's definitely not a directional derivative. If it were, the v would have to be out front. So it's neither of those cases, but I do want to bring to your attention that it does kind of look like this. Our function we wish to transform looks like this. Right? But that the one that I've given you here, this is already in the transform space. It's not in the natural space. So this is where it's to our advantage now. We can take that perspective that I said before. The only difference between the transform space and the natural space is a complex conjugate. And we'll see that a complex conjugate of that to that is actually going to bring us back. So in fact, what we'll be doing is the reverse direction. So we will transform in the reverse. But I'm not going to go through that. That's a lot of cognitive strain that I realize you're going to have to get used to think about how we're going to be doing this in the reverse to end up with a shift. But technically the shift is in the transform space. We're not going to go through that. What we're going to do instead is we're going to utilize these properties of the table itself. So what I'm going to do is I'm going to say, hey, I've got a complex exponential here and I've got a Gaussian. Let's jump up to the table and see if we can find them. So we're going to jump up to the table and we're going to say, these are the real functions here. We've got a Gaussian and we've got a complex exponential. So they do both show up on the table, and that's going to be to our advantage. We would love to just go beep bop, and bring them over. I would love to just do something like I v dot x multiplying e to the minus x squared over 2. I would love to say that this transforms to, what is this ugly looking thing, 2 pi d over 2 delta y minus, now let's keep in mind that the vector I'm looking at here is actually a v, so y minus v, and then what would the Gaussian turn into? It just turns into a Gaussian e to the minus y squared over 2. I would love to do this, okay? Would love to, but it's just a little more complicated. So linear functions behave well with addition, subtraction, and multiplication by constants, but linear maps do not behave well with multiplication of functions themselves. So what's going on with this multiplication is that this multiplication actually maps to not a multiplication here, it maps to a convolution. So what I'm going to have to do is perform a convolution of those two functions. And underneath the convolution, I will recover my answer. So let's just scroll up and see that, because I've included it here, and jumping back to your Laplace transforms, you've probably remembered convolution. So I've included the convolution up here. There it is. Here's my multiplication of two functions, and they turn into the convolution of two functions. What's the convolution look like? This is what I'm thinking. 1 over 2 pi to the d over 2, and then the convolution is an integral where one function takes in the integration variable, the other function takes y, that's the variable going into my convolution, and then minus the integration variable. So I've got 3 sets of integration variables, if you include the d, c at the end there. And then there's one copy of y, which is the input to the convolution. So let's just kind of take a quick mental snapshot of what that convolution looks like, and then jump down back into the problem where I actually want to compute this. So here with the sign, we're going to say, hey, the complex exponential maps to the delta function. The Gaussian maps to the Gaussian. What does the convolution of the delta function with the Gaussian look like? Well, here it is. I've written it out for you. So the convolution of the delta function, right? So I put a hat over the one term. So that's the delta function. And I've shifted the delta function by v, right? So this v right here corresponds to that v right there. And then the exponential here is, or the Gaussian is the term that's going to turn into the Gaussian over here. And keep in mind the convolution formula. That's where all of this is coming from. It's 1 over 2 pi to the d over 2, integral over all of space. And the convolution formula says it's phi hat xi. I know x's are kind of my worst Greek letter to draw. Phi hat of xi against phi, other phi, two versions of phi of y minus xi, d xi. So that's what the convolution looks like. Now the fact that the v is there comes from the v in the complex exponential. The fact that the xi is there comes from that x is actually turning into xi for the convolution, and then this entire x becomes the entire y minus xi because that's the entire term there. So this xi corresponds to that xi, the v corresponds to this v, and this x corresponds to the full y minus xi, which is there. So that's where the convolution comes from. It looks a little bit ugly, but once we set it up, we can actually use our properties of the delta function. This is very useful. Let's jump back up to how the delta function actually gets defined up here. The delta function is literally defined as if I take a convolution against it, then I just evaluate at the point that's not the integration variable, right? There's a bunch of integration variables away. I look at what's not the integration variable and I evaluate there. So I'm going to look at everything that's not the integration variable inside of delta. Here we are. The one that's not the integration variable is v, right? Because the integration variable is c. So the one that's not the integration variable is v. I'm going to evaluate v into c. And when I evaluate v into c, I'm left with e to the minus y minus v squared over 2. So that's going to be the Fourier transform of just one of these two terms. It's Fourier transform of this term right here. I have to repeat it for the Fourier transform of this, but notice the only difference is that that v becomes a negative v. So instead of having my Fourier transform where I end up with a negative v, I'm going to end up with a positive v. You'll notice a little bit of a LaTeX typo there. So I'm going to end up with a positive v instead of a negative v. And then if I recombine, right, the Fourier transform from the beginning, I just wanted to transform this. That was the one with the negative v. This, that was the one with the positive v. And then I'm just going to bring the 1 over 2i's and the minus sign along for the ride. And we end up with our overall Fourier transform, which is just a linear combination of shifted Gaussians. So that's how we can use the table in a second setting. Anyway, that's all I've got for you all today. We're going to get a lot of practice with this in class. It should feel somewhat similar to the Laplace transform, just now with some complex exponentials instead of regular exponentials. But I'll see you in class and we'll practice. Bye.